It's probably best if you just stay there and be confused. Where am I? Okay. So, what do we have? Okay, we talked about dual ignition. Oh, we got 2 spark plugs, 2 sets of spark plug wires, 2 magnetos. Why do they do that? Why 2 of everything? So they can make more money selling you parts.
Yes. Big spark plug.
Yeah, it's the what? It's a what?
It's a big spark plug.
The big spark plug, not a big spark. It's big spark plug. It's the people. Bringing down the man, or the man bringing us down. Okay, so operating theory. Am I on D? We'll go D. Operating theory. All right. Question number 1 in this oral. There are 3 circuits. 3 circuits in a magneto. What are those 3 circuits? Magnetic circuit, the primary circuit, and the secondary. All right, let's talk about the magnetic circuit. Magnetic circuit consists of which parts?
Magnet, the full shoes, the full shoe extensions, and the coil force.
All right. Consists of I kind of take a while to get through them all, but whatever. Consists of a rotating magnet, all right, and the rotating magnet is on a shaft that runs the whole thing, right? What turns the rotating magnet?
Cam. Oh, wait.
I like the engine is the best answer.
Good job.
It's timed off of the cam, but it's not necessarily run off of the cam. You guys built a Lycoming engine. It actually runs off the idlers.
Oh, yeah.
Yeah. So it doesn't have to run off the cam.
Cam by proxy.
Cam by proxy, I'll accept that. But it doesn't necessarily run off the cam. You have to think about it as time to the cam and also time to the crank. You know, the whole thing goes together. But it's not necessarily run off the cam. It is run off the engine. It's run off the accessory case. It could be one of many different gears back there that's actually running it. So I would not necessarily always say it's the cam. Some engines it definitely is. Some it's definitely not.
Maybe that should just be engine.
I would just say it's run off the engine, the accessory gear train. Yeah, because if you say it is run off of the cam gear, you could be wrong a lot of times. So what are these magnets? The magnet can be a 2, 4, 6, or not R, or even an 8-pole magnet. That's a lot of poles. A 2 or 4 pole is most common. I would say the 2 is really the most common. The rotor, what's the rotor?
The thing that the magnet is on.
The thing that the magnet is on is correct. The rotor, love it when we use things. Rotor is made from alnico. A-L-N-I-C-O. Alnico. What does that mean? So Al is aluminum. Ooh, I like that. Aluminum. Well, it's aluminum alloy, so it just means it has other stuff. Let's see, Yeah, the name's kind of tricky. So Al, and then what do you got? Nickel and
Cobalt.
you guys are good. Except they threw what in here? Iron.
Okay.
So that wouldn't be alnico. It'll be alanico or alfanico. Alfanico.
Yeah, he's the guy in the
Alfenico. Alfanico. But they threw iron in there. But otherwise, you would have been absolutely right. Nickel and cobalt. And cobalt. What do you suppose? Does it have high retentivity or low retentivity? Okay. Has very high retentivity. Which means what?
Once it's magnetized, it stays magnetized.
It stays. These are hard to get demagnetized. They do not like it. All right.
2008.
So we have the rotating magnet. We have the pole shoes. The pole shoes. Let's see. So the rotating magnet rotates in the pole shoes. I don't have a case here that's been taken apart, but those are those. If you look inside of your magneto, you will actually see it. You have the rotating magnet with your north and south on there that sits inside. We'll make it a different color. Sits inside pole shoes that kind of come around. And they would look a little bit like this. That would be a pole shoe right there. So one on each side, the pole shoes. And what do the pole shoes do?
They complete the
magnetic flux.
circuit.
Well, it's going to take the magnetic lines of flux and, well, I guess we could do it this way. No.
And that's how they flow, right? North to south and the motion.
So right now I've got pole shoes. So I need a circuit. I called it a circuit. Circuit means a what?
Half.
A path. So I got a path, goes from north to south. Do I have a path?
No.
I don't have a path, so I'm obviously not done yet. So I got pole shoes. Pole shoes are laminated sections of soft iron. Okay, now why is it soft iron?
So it can be easily magnetized and remagnetized?
Can be easily magnetized or remagnetized. And also, does it keep its magnetism?
No.
That's good, right? So laminated sections of soft iron. Why laminated sections?
Prevents any
Okay.
currents.
Laminated to prevent eddy currents. And it has high permeability. Which is a magnetism term. It means that it's going to accept magnetism very, very easily. High permeability and low retentivity. All right, what comes next?
Pole shoes.
Yeah, wait, yeah.
Permeability by like absorption? Is that what you mean by like permeability? Like how
Yes, like
certain
that.
things are permeable and
It means
others-
that the lines of flux can easily flow into it.
Pole shoe extensions.
What is this pole shoe extensions you speak of?
An extension of the pole shoe.
Well, that is correct. So now, a lot of you have not said this in the oral, but now you have to. Pole shoe extensions.
Sorry, guys.
And the pole shoe extensions are just an extension of the pole shoe. That's kind of weird. So they just go right here. So it's all one thing, really, but I made it in two because that's the way I drew it. So pole shoe extensions. There, that's one thing. That's just that part. And it's all one piece right there, but they call it a pole shoe extension. Pole shoe extensions. So it allows the lines of flux to be transferred from the pole shoes to the coil core. To be transferred from the pole shoes to the coil core. What's next?
Coil core.
Okay, so the coil core, I'll pick a different color here, sits right here. And what is the coil core made out of?
Soft iron.
What kind of soft iron?
Laminated.
Laminated sections of soft iron. It's right there inside the coil, and it sticks out of the ends, and you can see all the laminations that are coming out of it. So right there, it just sticks out. So there. Now I've got the pole shoes, pole shoe extensions, and the
Coil core.
coil core. Coil core. Made of same material as pole shoes, and completes the magnetic circuit. And completes the magnetic circuit. All right, looking back here at the drawing. Is that big enough for you guys to see up there? I'll make it bigger. It'll do? All right. So when the magnet is inside of there, you really have, well, obviously it's got a lot of positions, but there's two positions we've referenced, the full register and the neutral position. So in the full register position, like I've got it drawn here, the lines of flux will come around, pole shoes, pole shoe extensions, coil core, back around into here. Okay, so you have all the line of flux flowing through there. And at that point, it'd be called full register. And then in a little bit, it's going to turn, and the magnets are going to be different. They're going to be, oops. Like that. North here, but south here, whichever way, it does not matter. And it's shorted out. So all the lines of flux just go like this. So nothing goes through the coil core. All right, so it's going to do that. And as it does this, you're going to see it right here at the neutral position, which will be 0 lines of flux. And then as it rotates, it'll go up to full register. And then it's going to keep turning until it gets down to, which is neutral, back the other way to full register, and back towards 0. So one full turn right there. So that's what's going to happen. And so this is not current flowing. This is what? It's not current, it's not voltage. Just lines of flux. Can you get shocked by this?
Yes.
No.
No.
From what? Shock you with my magnet?
It almost.
It might activate the vaccine.
They're on to us, run. Did I hurt? Did I shock you with my magnet? No, he activated his vaccine though.
Well, he's turning red.
Oh,
He's turning red.
Well, he's not clucking like a chicken, so I don't think so. So
Not yet.
down the right over. Okay, so no voltage, no current, no shocky. It's just a magnet running around in circles. That's all it is. All right? So magnets. So is any voltage here? No. So stop telling me that. And your orals. Well, then because then it goes through, and then you get the voltage in the coil and the core, and I'm like, what? Okay. Huh? Yeah. So we have no voltage, no current at all. There's none. We just have magnetism building up and collapsing down. Now, of course, I drew this thing right here saying, okay, well, it goes full register and down, and hopefully you could understand at one point the lines of flux at neutral here are just kind of flowing around doing nothing, and then at full register, they're going to come up and they're going to go through this the coil core. But as it goes through the coil core at full register, it flows out from there. right, at full register. So if I were to just look at the coil core itself and say, okay, this little graph I drew here, this is the magnet going around and, you know, full register, neutral, full register, neutral. Now I'm going to turn it around. I'm going to say, I'm going to put this magic, well, it's not a magic device. It's actually a Gauss meter, and I have a very expensive one we could bring in. And I hadn't thought about that because it's kind of new. And if I put it on this bar right here, and I turned this, and I had my very expensive flux meter, and I watched it, what would my flux meter show me right here that is happening as I rotate the magnet?
Collapse.
Well, it would look a little like this.
Wow.
I know, well, how'd I come up with that? So what's happening is through the coil core right here, it just transfers the magnetism and it expands and contracts and expands and contracts. This following suit with what's happening through the rotor, doing its thing, right? So expanding, contracting, expanding, contracting. Now, what is the frequency though, Kenneth?
However fast the engine is turning.
However fast the engine's turning. Faster I turn it, the closer this is going to get to it. Slower, the wider it's going to get. What about the height of this?
Yeah.
It should be the same.
Yeah.
Turning it faster is not going to create more magnetism. It's just the magnetism's there. Even I had to think about that one for a second. What to do? So, okay. So, all right. So we've got that going. I think I accidentally hit Control Z too many times and erased a bunch of stuff here. Sorry about that. Oh, we could try it this way. Circuit. We'll just go to circuit then.
Primary circuit.
Pull shoes, pull. Okay, coil core. Sorry, you lost. Oh, that's right there. Okay, and then operation. Operation. So what does it all work together? So this is pretty much what I just pointed out. So as the magnet rotates, the magnetic lines up. As the magnet rotates, the magnet lines up with the pole shoes and completes the magnetic circuit. This is known as full register. So as the rotating magnet rotates, the magnet lines up with the pole shoes and completes a magnetic circuit This is known as full register. Full register. So at this point, which is full register, maximum lines of flux travel through the pole shoes and coil core. At this point, max lines of flux. Lines of flux travel through the pole shoes. Pole shoes and into or through the coil core. As the magnet continues to rotate, the lines of flux decrease. Through the pole, through the pole shoes, and then the coil core. Coil core. And there will be a point where the magnet reaches neutral and the lines of flux do not travel through the poles. At the point where lines of flux do not travel through the coil core. Point. It is called neutral. It's also said that the lines of flux are shorted out at that point. As the magnet continues to rotate, the flux lines reverse and build back up. So as the magnet continues to rotate, flux lines reverse. Reverse and build back up. But in the opposite direction, in the negative direction. If we graph this, it looks like AC, and it is known as the static flux curve. You good?
No.
Oh, okay. Okay, so we got the rotating magnet, we got the pole shoes, pole shoe extensions, and the coil core make up the magnetic circuit. All right, now we've got the primary circuit, which consists of
Primary coil winding.
okay, primary coil winding. Now, in the book, of course, it would be kind of drawn over here, but let's try and do it this way. I may regret it. Because where is it really? It's wrapped around this. All right, and so, huh?
Not many wires, but
Not many. Not many. Let me think. So I want to make sure that's grounded. Bring it out of this way. What comes next?
the breaker points.
Breaker points, condenser, and breaker points. And a cam to open and close them. All right, so what happens?
Do we have a switch too?
You don't have to. I can put it in. Actually, I don't want to put a switch in, do I? The reason why I don't want to put a switch in is because I want to get in your head that
It's not directly in the
There's no switch directly.
magneto? Where's the switch?
Yeah, you're right.
Where is it?
There's not
Well,
one.
isn't it technically the breaker point?
It's in the
Would
Nope.
be-
It's a Pee-wee, right?
Where's Pee-wee?
No,
Is there a switch in this?
Oh, the switch is the outside connector.
Where's the switch?
The ignition
No
switch.
flash.
It's the key.
It's in the
Huh?
cockpit.
It's located in the cockpit. It's not on this. There's no switch.
Yeah, you're right.
There's no switch. Is this magneto on or off right now?
It's on.
It's on. If I install it, it's on. How do I turn it off?
Ground it out.
Ground it out from this right here. So if I take a wire, one of those little wires that you guys messing with all semester, just connect it from here to here, it's off. But as long as that's open, this is on. So that's what I say, propellers hate you and want to kill you. Because all it takes is for this wire to be missing or broken or some other problem in the ignition switch, and this is a hot mag. And how fast would I have to turn the propeller through to get the engine to fire?
Not very.
About that fast. Because no matter how fast or how slow you move the propeller through, I give you $100 if you can move it slow enough that it doesn't engage this impulse coupling. Anybody up for the challenge? You got to turn it in the direction of rotation.
Oh, that's the odd way.
Yeah. Okay. No matter how slow you turn it in the direction of rotation, if it's got an impulse coupling, it will eventually go far enough that it clicks. And if there's fuel and air in there, it's going to possibly kick right then and there. Yeah,
Have you ever hand prop a plane?
all the time. I worked on all kinds of planes that need to be hand propped.
That's scary.
I won't do it. I absolutely would just not do it. I have horror stories from that. Ugh. Want to hear my horror stories?
Yes.
Yes.
Oh, we'd love to.
So,
Just wrap a rope around it and then stand away and hold it.
I know. Why didn't we do that? Yeah. So, horror story number one is I was working in the machine shop, and my friend came in and he was going to go flying somewhere, and he was going to take the Aranca Chief. And the Aranca Chief had an A65. Well, this one was big horsepower. It had an A75. I converted it, 75 more horsepower. So it's like a rocket ship, man. They have no starter on it. Back in the day, they had this weird starter. There was a little thing in the cockpit, little handle that you pull like this, and it would go through a bunch of cables, and it had a little thing that would push on little something on the back of the propeller, and you pull it, and it would just kind of do that until the propeller would go around and kick. But that was long since been removed. So anyway, I was just doing my thing. It was a summer day. I had the door wide open. No, I didn't have the door closed because it was a cool day. That's right. It's part of the story. And so I was doing my stuff, and it's just like where my shop was. It's like there's an airplane, then an airplane. It's right there, very, very close. And I heard the airplane start, and then I heard it stop, and then I heard my friend screaming my name. And I'm like, oh crap, this can't be good. And so I opened the door to come around, and he came running in, and he flopped down on the floor right in front of me, and he's holding his hand and stuff. And I'm like, oh, the prop got him, and it did, it got him. And so I put him in my car, rushed him to the emergency. I didn't want to look, but took him to the emergency room, and it got him his hand really bad. It wasn't a bloody mess. It cut him, which was kind of weird. It's just a weird looking injury, but he had multiple surgeries, and last I know, he could only close his hand like that, which is hard because he's a computer programmer.
Ooh.
So,
Digitypes.
yeah, that's how I type. I type like I'm very mad at my keyboard. I had another one. It was funny. I did a top overhaul on a World War II. It was a Ryan something with a 5-cylinder engine on it, and I did the top overhaul. You probably know the guy. It was over at Executive, and so I get that thing all put together, and my boss, he was the designated hand propper. He was good at it. And so, man, I was in the plane. I'm trying to start it, brand new cylinders, and this thing wouldn't start, man. He's just pulling it. Finally, the owner shows up. I mean, this guy's like, he's in his 80s, man, and he just jumps up on there. All right, this is what you're going to do. And he tells me, give it 3 shots of prime and put the thing here and give it this way and put the throttle right there. And then when I tell you to, you're just going to put it on the, mags, and we're going to go. Okay. So he walks around the front of the airplane, and I mean, we've been trying for half an hour to get it started. And man, this old guy, he just pulled it through like once or twice, and this engine just took off at like 1,500 RPM. And I saw him nowhere. And I'm like, well, what do I do now, man? I'm not going to shut the engine off because I got to But I mean, it was a long time. I thought I killed the guy, and eventually just kind of came around. I kind of, damn man, don't leave me hanging like that. I'm like, I thought I killed him, but I was happy that the engine worked. You know, it's a bittersweet victory.
Silver mechanic completing the break-in run.
Yeah. I figured they'd kill me if I shut it down now. How many guys are going to kill to get this thing broken in? Yeah, my boss, he would hand prop anything. It was a horror story. And this story would take the rest of the night, but I'll just give you the
More notes.
Nah, yeah, but we had a Bonanza that just turned awful, and it ended up, it's an awful, awful story, one of the worst days of my life. But before that day, we put a new prop on an airplane that the pilot had done some bad things, and he landed in Rio Linda with the gear up. No, he didn't land with the gear up. He was going to land with the gear up and whacked the prop down the runway, and then took off and went around. And then he landed with the gear down at that point. And so we were going to do, well, I did a prop strike on the engine, but to get it to our shop, we got a new prop, put it on, they got a ferry permit, and then my boss went to fly it, or somebody's going to fly it, and starter didn't work. It was on a Bonanza. It's a 6-cylinder engine. You don't want to hand prop a 6-cylinder engine. They suck. But my boss, being the guy who would do it, man, he, all right, I'm going to get in there. And the pilot said, hey, be careful, man. There's something wrong with this switch. I don't know what the hell's wrong with it. I can't tell if it's on or off or what the hell. And so I think it's off. And my boss pulled it through a couple times. It went around and whacked him hard. It didn't, hurt, but ended up at the NTSB crash site later on, much later on, like a month or two later. That was the first thing the NTSB said, and they stuck their head and they goes, geez, man. He came out of the airplane. I was standing there. How many freaking positions is this thing supposed to have? I think I last counted 13. It should only have on, off, start, right, left, but that airplane ended up crashing. I'll tell you that story later. So, all right. So we got the primary, which is attached to the magnetic. So we've already established the fact that as the magnet goes around, there is no current flowing through the pole shoe extensions, or the coil core. Is that correct?
Correct.
Zero current, zero voltage. It only has magnetic lines of flux, which go out and in, and out and in, and out and in. And that's all they do is go out and in, and out and in, and out and in. So it goes out. Now when it goes out, what does it do? Expands, and it cuts across the primary coil. We have magnets, and we have wire, and we have let's get my Tinker Toy thing. Magnets and wire and movement creates voltage, right? So the lines of flux cutting across the primary creates what in the primary? Voltage. Voltage means we have current flow. We have current flow. So now we have current flowing through these windings.
Yes.
Good, I'm glad you agree. Okay, so it's very important to me at this point. Make sure I'm right. All right, so we have current flowing through this coil, which makes the coil an
Electromagnet.
Thank you. Perfect word. That's the word I wanted here. Makes it what?
Electromagnet.
Electromagnet. What's an electromagnet?
Something, a magnet.
What is what part is an electromagnet?
Where the current passes through, it makes sense.
Yeah, what part on here is the electromagnet?
Oh, the
Primary
primary
coil.
The primary coil is an electromagnet. So how many magnets do I got now?
Two.
Two. Okay, well I got the primary, so I got the coil core, which became a magnet. It's not an electromagnet. It's not really a permanent magnet. It's a magnet that has lines of flux doing it. Now I got this primary coil, and it's a magnet. What? Oh, you're just cracking. Okay.
Yeah, no,
You're
the
cool.
question's coming, but if...
It's coming. You don't know what it is yet, but it's coming.
No, I know, but I want to...
Stay tuned. Stay tuned. Okay. So we got that going. So if I had to draw, and I don't have to, but I will, if I had to draw kind of what this looks like, this in the primary, what it looks like if I were to measure the voltage going, or the current, or even the magnetic lines of flux, if you will, it would look a little like this. but symmetrical. That should be your question. How come on the downside it looks like it's,
It's got a little lobe on it.
I know. So that's what it would look like if I just let it run and I didn't consider the breaker points or the capacitor or anything else. It would contract and expand and contract and expand. So that's just what it would do. But I'm not going to let it do that. I'm going to modify it. Modify. So it's not going to look like that. It's going to look a lot different. But I want to draw it on its own because now we have other components that are kind of messing with it. So we go back. I should have just left it. We've got this blue. Blue can be my magnetic lines of flux. And where are they flowing? Where's the magnetic lines of flux?
Into the primary core.
Just the purely magnetic, which is the blue.
They're coming across the core.
Okay, well, they're going through the coil core, expanding across the primary. Okay, so the primary, of course, it's going to get its voltage and its current starting to flow. And what it wants to do then is tends to follow it, but it's a little bit slower at that because of Lenz's law. It doesn't quite want to do it all on its own. It sort of waits because as it builds up, as we have I shouldn't use it because I get mad at you. When I have the magnetic lines of flux here building up and it's telling the primary coil, hey, or inducing this voltage, I got this voltage, so great, voltage starts to flow and it builds up and voltage is flowing. We'll follow it here for a second. It's flowing, awesome, and it's supposed to start going down, but what was Lenz's law going to tell my primary coil, what's going to come into play there? So rather than dying, it's going to say,
Stay here.
"Now you stay here. Wait a minute. I'm going to tell you something. I'm going to show you something." So it kind of waits. What? Okay, so I'm going to wait. What do you want? You know, it's like kids. Nothing. Never mind. Okay, so now it's going to start to fall off. Well, if I could make it so that it didn't just follow it, because I guess that's really what it would do. It would follow it. Say, oh, well, what's going on over here? What, we're going to change direction? Well, I'm going to stay here for a minute. No, fine, so now we've got that. Well, I don't know, that's not going to really do anything for me. It's got a nice change here, but not really. But we've talked about this idea of E gap, which is the efficiency gap, also defined as,
10 degrees after the neutral.
well, not 10, because it could vary by magneto. One magneto may say, oh, we're 8. Another one may say 6. This one says 10. Another one's 12. So it's the number of degrees past neutral. Where's my neutral point?
0.
0. Number of degrees past neutral at which
Points open.
the point's open. So let's just say it's 10 degrees right here. That might be a little much, but it's easier to do that. So that is going to definitely change this. Well, it's not going to look like that anymore. Because, and I do have that out just a little bit, so not to scale. So I've got, this is happening, and while it wants to hang on, what they say, they, whoever they are, the people who write the books, this difference between here, this blue line, and where this is, that creates stress. It's like the coil's holding on, but everybody's left it behind. It's like, no, I don't want to change. I hate change. Change is bad, right? And so you create this stress here. But, and I got to extend it out because I'm not exactly to scale, but where it would normally start this slow curve down, we're going to open the points right there. And so when I open the points, you got nothing. You have an open circuit. It's off, right? So down. So when it comes down like that, that is this rapid movement. There we go. Down to here. Super rapid movement. Now notice a couple things. One, we've got to wait until we have a difference between here and here before it really works well. So it does work well. Magnet's already down to neutral, and it's past neutral. It's starting to turn around to go the other way. Open the points over here. If I open them too soon, I'm just going to go like that. That doesn't help. Open them too late, and this is already starting to fall off the curve at that point. So you got to get it when you have the most stress, right before this wants to really start to fall off. and then it's going to come down. So that's why we open the points way down there. So we open the points, and then of course the same thing's going to happen, but in reverse. And then it's going to wait for a while, a couple degrees, 10 degrees past neutral, and then bam, it comes up. It's harder to draw up.
It goes backwards. Yes,
Because
sir.
it does. It goes backwards. Because it does. Because it doesn't care. You just turn the computer screen upside down. It looks the same. So it's going to go the other way. So that's what's happening right there. So now want me to write notes about it?
Sure.
Yes.
The primary circuit.
You have a choice. I can either write notes or Zach wrote a song about it. He can sing it.
Do it.
He's still working on it. It's a work in progress. All right. Did I write primary circuit yet?
No.
Is it F?
Yes.
Primary circuit consists of the primary winding. Hey, which circuit does the coil belong to?
Secondary circuit. Well, all three of them.
All three.
All of them, because it's got the
Primary one.
coil core, which goes to
The primary.
the magnetic,
Magnetic.
the primary, which goes to the,
Primary.
and the secondary, which goes to the
Secondary.
primary winding. It's contained in the coil assembly. And has relatively few turns. That's relatively. Few turns of insulated copper wire. And then we got the breaker points. I'm just going to move up a little bit because it's time to go. What parts make up the secondary or the primary circuit? What parts?
The capacitor.
Capacitor.
Points and
Breaker
cam.
point.
Breaker points.
And the
Primary
cam.
circuit.
We could say cam if you wanted. And
Primary winding.
primary windings. Do I have a complete path? Yes, I do. From right there around over here. So there's a complete circuit going through there, plus a capacitor in parallel, which works. If you put it in series, not so much. So, all right, that is it for tonight.